so you have like 6 Christmas presents, and you have 5 different piles to put them in. What do you really care about? How many are in each pile, exactly? That's what you care about. The piles aren't in order though, but you just want to know how big are the piles. So for example, one way to do it would be to put all 6 objects in one single box. Okay. Another way to do it would be to say, I'm going to put 5 of those presents in one box and 1 present in another box, but I'm not keeping track of which box is which. But I just basically am breaking it down as 5 and 1. Everybody see that? What else could we do? 4 and 2, exactly. So 4 and 2 would be another choice, right? So I could have 4 objects in one pile and 2 in another. So what do you see that I'm doing here? It's partitions of the number 6. It's a number of ways of breaking it down. So we could do, 4, 1 and 1. Or we could do 2 piles of 3 each. We're just simply caring about how many things are in the piles, right? By the way, 2 and 4 is the same as 4 and 2. That's because you don't care what's first and what's second. Everything is completely unordered, so I don't have to write that one down. I'm just writing down the partitions. So what else would I have? 3, 2, and 1. Okay, what else would I have? 3, 1, 1, 1. Okay, what else would I have? 2. Okay, let's do this in an order that we won't forget something. 2 and 2 and 2, right? Let's add up to 6. Okay, what else would we have? 2, 2, 1, 1. All right, what else would we have? 2, 1, 1, 1, 1. Okay, what else would we have? 1, 1, 1, 1, 1. I only have 5 boxes, so all 1s wouldn't work. Okay, you guys are good at that. I thought most people would miss that point. Okay, good. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 ways to do it. Okay.
Is that how that problem is done?
Huh?
Is that how that problem is done?
That's how that problem is done. So I just did it. Huh? No. This is not any. I mean, this is not something that I specifically lectured on. It's just, but it's a problem that you can just think about and figure it out. Yeah, it's related to the Stirling numbers. It's related to the number of partitions of n, which is something I haven't focused too much on. And in this case, we're not getting all of the arrangements because we have to throw some of them away. So, I mean, okay. So this is not a bad thing to show you guys. If it's something that is reasonable for me to ask you. Maybe I never did quite talk about this, but if I feel it's something if it's combinatorics, if it's something doable on the fly, I won't hesitate to ask you about it. So this would be an example of something like that. Yeah, Laura?
Could you put like part B, but then on order boxes by dividing by 5
I don't think so, because dividing by one clean cut number is going to be hard to do, because it's going to depend on what the distribution was in the first place. Yeah, I don't think. This is by far. This is the only way I know of how to solve the problem. If anybody has another way, I'd love to hear it. But this is the only way I can think of that would be the right answer. It's just the partition. It's just the number of ways of breaking down 6 into a bunch of pieces. That's it. Okay. All right, let's move on. Let's try another problem. Call this number 6 here. All right, this is a nice problem here. What is the fewest number of time slots needed to schedule final exams 417, 425, 430, and 471. If there are no students in both 302 and 471, there are no students in both 402 and 471. There are no students in both 414 and 417. There are no students in both 414 and 425. No students in both, sorry, there's a lot of writing here. It's all typed up on the handout. If you don't want to write this all out, I do apologize. No students in both 302 and 402. No students in both 302 and 407. And no students in both 407 and 414. They have no students in any of those pairs, okay? But in every other pair of courses you could consider, there is a common student in both classes, okay? So, but there exist common students in every other pair of courses. All right, so this is a nice question. So how many courses do I have listed here? I'm just curious. 2, 3, 4, 5, 6, 7, 8 courses. So if there's 8 courses, by the way, how many pairs of courses are there? 8 choose to, which is? 28. Yeah, 8 choose to, right? 8 factorial over 6 factorial, 2 factorial, right? Another way of thinking about it is 8 times 7 over 1 times 2. Remember, it's not bad to be able to do this mental math really fast. Basically, you factorial your way down from the top this many steps. So 8, 7, and then you factorial up from the bottom the same number of steps. Okay, so there's 28 ways that we could take pairs of courses, and it looks like I've said something about 7 of those 28 pairs or whatever. So in a worst case scenario, since there's 8 classes there, you would need 8, you could use 8 time slots. So if I did 8 time slots, we would not have, there would never be a problem, because you just give this final during the first time slot, give this one during the second time slot, give this one during the third time slot, and so on all the way down the line. Nobody can have a conflict. If you only offer one final at a time, nobody can have a conflict, right? But then you start to think, well, wait a minute, since there's no students in both 302 and 471, I could give that final at the same time. I could give those 2 finals at the same time, and there would be no student who was, in trouble. Okay. So I want you to think for yourself. Don't say it out loud yet, because this is the key thing, is what kind of problem does this have to do with? I'm going to give you about 30 seconds to a minute to think about what topic is this dealing with, now that I've sort of framed the question for you. hand if you think you know what topic this has to do with. Okay, Nyla, do you want to give it a go? Forbidden positions, okay. So you'd have to somehow put, well, how would you set that up as forbidden positions? So you have rows and columns, right? You put those X's in the grid. How would we do that sort of with this information, do you think? Okay, that's fine. That's fine. Okay, so does anybody else think they know either what this has to do with or have a suggestion for how to push this forbidden positions idea further? I'm going to actually disagree with you, but we are going to see forbidden positions today. So keep that in mind, it's coming. Let me do this. See if this gets you thinking a little bit. Now, what are my classes? I don't even know. So, better marker here. Okay. 14. You can. Yikes. At least it didn't break my ankle again. 425. I'll be ashamed. 430 and 471, right? Okay. So I'm drawing vertices, right, on the graph. What do you think, Ron? Coloring of a graph, right? So, for example, 302 and 3, let's see, what's a good example? 302 and 430, I'll just take that as an example. There is some common student in, because it says there is a common student in every other pair. So 302 and 430, there has to be a common student. So what I can do is I can draw an edge there. And as Mark is saying, remember what our rules are on a coloring? When you color a graph, two vertices that are connected by an edge cannot be the same color. The colors can just be thought of as the time slots for your finals. So the courses that are colored red have finals on Monday morning, and the courses that are colored yellow have finals on Monday afternoon, and so on and so forth like that, right? And if two things are connected by an edge, then that means that they can't be the same color. You see how that becomes a chromatic number problem? It doesn't look like it at first, but that's exactly what this is. This is a chromatic. This is a problem. Basically, we need to draw this graph and find its chromatic number. Okay, so you guys are going to have to help me because normally there would be 28 edges on the graph. That would be the complete graph, K8. K8 would have 28 edges. I'm going to remove 7 of those edges because I won't put an edge. There are no students in 302 and 471, so I don't have to draw a segment between those two. So, but I'm still going to need to draw the other 21 edges. Okay, so can you guys help me? Which classes can I connect 302 with? 425, 414, and 417. That's it? So the ones that are not connected, I'm not done yet. I have a lot more to go, but just the 302. So there is a common student in, there is no common student in 302 and 471, right? And there's no common student here and here in 402 and 302, and no common student here and here. Agreed? Go ahead. We could draw the complement of the graph, but then eventually I need the chromatic number of this graph. So we haven't really done anything. I'm not sure if there is something. I haven't think about that. Whether you can say something about the chromatic number of a graph by instead looking at its complement. That's not clear to me at all that there would be that think we should just draw this one here, but it's a good thought, because it would be a lot less lines. Okay, how about for 402? What can I connect 402 with? Okay, that means there is a common student in 402 and 407, right? Okay, what else? 414, all right. What else? 417, 425. All right, go like that. Okay, how about 407? So 407, there's no edge from 407 to 414, right? Or through it too. But everything else has to be connected. So 407 to 417, 407 to 425, 407 to 430, and 407 to 471, right? Okay. 414, there is no common student in, so I've already done these three, so I just have to look at the ones that are bigger. 417, there should be no edge there, because there's no common student. And 425, there should be no edge. But 414 and 430 should have an edge, right? All right. What else? 414 and 471? Oh, yeah. Yeah. Okay. Wait. Yeah, that's right. Okay. All right, we're getting there. So that was 414. So with 417, where does that appear over there? Only with 414. So it has to be connected to everything after it, right? So 425, 430, and 471. It's a messy graph. Okay. 425 has to be connected to everything after it, right? Here, and here, and then 430 and 471, there is common students there, so those have to be connected, right? Okay, basically, what this problem is asking you to do is find the chromatic number of that graph. Oh, by the way, how can I check and make sure that I got 21 edges on here? Right, find the degrees of the vertices. So this one has degree 4, this one has degree 5, this one has degree 5, this one is 4, this one is 6, this one is 6, this one is 2, 3, 4, 5, 6, 7, right? This one is 5. I hope I did that right. So I add up all those numbers. This one? 1, 2, 3, 4, 5.
Okay, can't see.
Sorry. So 5 plus 4 plus 5 plus 5, that's 19, 30, 42. Those numbers add up to 42, so that's 21 edges, right? Okay. So I got that right. Now we have to figure out the chromatic number. Okay. Any thoughts about how to do that? It's at most 8, because there's 8 vertices. I need at most 8 different time slots, but I think it's going to be less than that.
Is that most 7? Because the highest degree is 7.
We had a theorem that said that if you take the maximum degree of a vertex and add 1 to it, you get an upper bound on the chromatic number. So that was the delta thing. So if you take delta plus 1, of course in this case that's just 8. Delta plus 1 is 8, which means the chromatic number is at most 8, which means it doesn't tell you anything you didn't already know. Okay. What about lower bound? Okay, so we have this other result that the chromatic number of a graph is at least the ceiling of n over q. Of course, n here is 8. Q is the largest size of a subset where there's no edges among those vertices. So Q, for example, well, here's 3 vertices right here. Just happen to notice this. There's 3 vertices right here where there's no mutual edges. So Q might be 3. It's at least 3. If Q is 3, then this would be 8 over 3, and the ceiling of that would be 3. So the chromatic number would be at least 3. If we find a larger subset, let's say Q is actually 4 and we just didn't see it yet, well then our inequality, our lower bound gets worse. And we were saying the chromatic number is only at least 2. Honestly, this is not, I mean, I did go through this and prove it in class. It's not generally the most useful resort. Is there another thing we could do to try to come up with a lower bound on the chromatic number? Look at cycles. Yeah, looking at for cycles in the graph is really good. For example, right down here, there's a triangle, right? Triangle. If there's a triangle on the graph, you're going to need 3 different colors for those vertices, right? Okay, so of course a triangle is really just K3. What would be the next step up from a triangle? K4, exactly. Does anybody see a K4 in this graph? 430, oh, there's multiple. I see several. I see several of these, right? For example, I see, let me see if I can use a different color here. I see, for example, does everybody see right here 402, 407, 417, 425? And then it would cross, goes right there, and that goes right there. So the chromatic number is at least 4. You have to have at least 4 different time slots to give these finals. But the other thing I want to notice is that, notice that Math 430 is connected to everything. So if I was able to get a K4 that didn't use Math 430, then I could obviously make a K5 out of it. Because I will be able to make this edge go into all of those same vertices again. You see that? See, if you have a K4, there's K4, and then you have another vertex that's connected to everything else, that's a K5. Okay, so you need at least 5 time slots. Can we somehow, do we maybe need 6? Or can we get away with 5? So, so for example, this one could be red, yellow, green, blue, and white. I have to have all different colors for that. Let's try and reuse those colors again on the vertices. See, I've only got 3 vertices that are not yet labeled, right? So can I reuse some color? Like what could I do with 414? I could make it yellow because there's no edge here, right? So that's a safe way to color it. In other words, that just means I'm going to give the 414 final at the same time as the 425 final. And that's fine because there's no common students. You can see that over here. 414 and 425 have no common students. Okay? All right, what about, we just said these are the only 2 left. Can we use colors that are already on the board to color these last 2 vertices? Okay, so for example, what could I do for 302? White, okay, good. And what can I do for 471? White. I can do white again, right. So actually all 3 of these can be given at the same time. There you go. So, you see what I did? What we did there? We said the chromatic number has to be at least 5 because there was a K5 inside the graph. But then, by showing me a coloring of the graph, that proves that the chromatic number is at most 5. Guys, please be careful if I ask you on the test to tell me what the chromatic number of a graph is or the crossing number. Either one is always in 2 parts. You have to show me the coloring or the crossing that is the right answer, but then you also have to show me that you could not have done better than that. So here I've shown you a coloring with 5 colors, But I've also been able to show you that you can't do better than that because there's a subgraph of k by 5 inside of it. So this graph contains k5 as a subgraph, and you know what would be really good to do if this was on the test would be to tell me what are the vertices in the subgraph. So 402, 407, 417, 425, and 430. Those are your vertices that produce that subgraph. Okay. Thus, the chromatic number of the graph is at least 5. However, our coloring shows that the chromatic number of G is at most 5. So we've actually exhibited a coloring that uses 5 colors. Okay, so thus the chromatic number is exactly 5. Okay? So that's kind of how you would want to argue it. 5 times 5, that's what you have to have. But the first step is just recognizing that this is a chromatic number problem. It doesn't actually say it that way. It doesn't tell you that in the question, so you have to deduce that sort of for yourself. Okay? Any questions on that? The nice one. Okay. See, if you draw the complement graph, which would have been a lot smaller, I'm just not sure that knowing what the chromatic number of the complement graph is would tell you what the chromatic number of this graph is. That might be something for you to think about. I mean, I could ask that as a true-false item. The chromatic number of G plus the chromatic number of G bar, does it have to equal N, for example? Probably not. Probably don't. Right. This is really not a forbidden positions question. Because, I mean, you have the courses, but you don't have time slots established, right? You haven't said, I mean, if there had been something like, oh, I can't give the Math 302 exam between 10 a.m. and 12 noon, and I can't give, so that would be a forbidden position. Okay, there's time slots that I cannot give that exam. Right, then I could think about drawing my table. It definitely resembles a forbidden positions problem, but there's just no time slots actually established. So it's better to think of it as a graph. Okay? Another good example of something like this, maybe you could think about it, would be putting together the NBA season schedule. And, you know, one team can't play, you know, two other teams on the same night or something like that. So you could, like, have a vertex for each basketball team and draw a segment between them if they can't be playing each other on a certain schedule. So there's probably a lot of examples that chromatic number actually plays a role in. Okay, let's try another problem if we're okay with this one. Everybody understand it? Okay? All right, good. I'm going to go right to the next problem, number 7. Okay, so we're going to take 5 professors. And I just picked Annan, Edwards, Good, Jamshidian, and Solheim. Okay? And let's see. Want to staff MH McCarthy Hall from 10 a.m. to 3 p.m. as a welcome committee. So we're going to welcome the students to the building. And they're going to, as welcome to students, and they're going to do this in 1 hour